Okay. So, we are discussing the following question: when does an arithmetic function which takes real values, so an arithmetic real valued function, have a limit law? In other words, when does the limit as n goes to infinity of the proportion of natural numbers up to capital N for which the values f are less than or equal to z, so in terms of z, okay, when does, for every z, does this limit exist, and whether this can be expressed as a function is the question that we are asking. Now, there are many ways to answer this question, but one of the most important theorems in this direction is the following theorem of Addish and Wintner, which says the following. So, this theorem is from, it's a very classical theorem, it is from 1939, and it says the following. We will not be discussing the proof of this theorem in detail, but we will indicate where the motivation and key ideas of the proof come from. So, this theorem states the following. So, f from n to r possesses a limit law, and let us say this is, so they answered this question for additive functions. Okay. This possesses a limit law if and only if the following happens. If and only if, I will give you 3 different series, and we can find some region where those series will converge, simultaneously converge. So, if and only if the following series converge simultaneously for some positive constant r. And what are these series? The first series is the sum of the reciprocals of the primes. Which primes? All those primes for which absolute of f sub p is greater than r. The other series is summation f of p over p, where you run over all those primes for which absolute f of p is less than or equal to r, and summation again over all those primes for which absolute f of p is less than or equal to r, f of p whole square over p. So, if you can find at least one positive r for which all these 3 series converge simultaneously, that is sufficient and necessary to show that your function f will possess a limit law. Okay. So, we will discuss this in our next live session in detail. The motivation for this theorem comes from what is called the 3 series test in probability. So, we will discuss these details later. Now, if this happens, then the characteristic function of the limit law of this arithmetic function, so of the limit law is also called the limiting distribution function, okay, capital F, is given by the following product phi sub f of t turns out to be equal to product over all the primes 1 minus 1 over p times summation k going from 0 to infinity e raised to the I t f of p raised to the k, all of this is in the exponent, over p raised to the k. Okay. You will remember from de Lange's theorem that we discussed in the last few lectures, this infinite product is very similar to the mean value of some multiplicative functions you had obtained in terms of infinite products. So, there you had a multiplicative function which takes values in the unit disk. So, you had g of p to the k over p to the k. So, this is a specific example of that scenario, right. Now, why is this, what this is telling us is that the characteristic function can be written in terms of these exponential functions, and this is again motivated by the fact, by an important theorem that we learned, which was the following. So, recall by Levy's continuity theorem, you have the following. So, f, so any real value. So, here you do not necessarily need additive. Okay. So, a real valued arithmetic function has a limit law f capital F, if and only if the following sequence of functions converges. And what is this sequence? This is the sum. So, 1 over n times summation little n up to capital N, and you have e raised to the, so instead of to avoid confusion, we will just write it as exponential. So, exp of I t f of n. Okay. So, the sequence for capital N bigger than or equal to 1, if the sequence of functions converges as capital N goes to infinity, pointwise to some function in terms of t, let us call it phi of t, which is continuous at 0. This is another equivalence. And in fact, in this scenario, if this convergence is happening, then phi of t turns out exactly to be the characteristic function of the limit law or the limiting distribution capital F. characteristic function of the limiting distribution function capital F, coming from your original arithmetic function that you have started off with. Okay. Now, as we were discussing before, this leads to some interesting questions because of the fact that your exponential, if f of n is real valued, exponential of it f of n will lie on the unit circle. More generally, we can consider functions which take values either on the unit circle or inside unit circle. That is the more general scenario that we have been looking at. So, what we want to do is, because we want to check whether this limit converges or not. In a sense, what we are asking is whether the mean value of a certain function exists or not. What is the mean value? So, we have, so the question is more refined question. The kind of arithmetic functions that we are very much interested in this course are additive functions, in which case exponential of it f of n will turn out to be a multiplicative function. So, the question is, when does a multiplicative function let us call it G from n to the region, so the set of complex numbers with absolute value less than or equal to 1. The question is, when does such a function have a mean value? What is a mean value? Let us denote it by m of g. This is defined as limit as capital N goes to infinity 1 over capital N of summation n up to n g of n. When does this limit exist, or equivalently limit, you do not have to just, you can consider in general limit as x goes to infinity of this sum. Okay. So, our question is, when does this exist? And this is one of the fundamental themes in probabilistic number theory. And there are several beautiful results that answer this question. So, I am going to state some of them to give you an idea of the kind of results that exist in this field, and I will give you a very interesting application of one of these results to indicate the strength of these results. They are not just some trivial results, they are very, very deep, and they lead to very fundamental theorems in number theory as an application. Okay. For example, the prime number theorem. So, I am going to discuss that. So, here is a theorem of Versing and Addish from 1968, okay, which says the following. So, let us take G multiplicative and absolute G of n is less than or equal to 1 for every n. Okay. Then one can show, so if you can find some real number t such that the following limit exists, or rather the following series converges. So, if you can give me some real number t, whether 0 or non-zero, just some real number for which the series given by 1 minus real part of g of p times p raised to the minus I t over p converges, then your mean value exists, and in fact 1 over x summation n up to x g of n can be written as a certain complex valued function. It turns out to be equal to x raised to the I t over 1 plus I t, okay, for every so if such a t exists, then in terms of that t you can give me the mean value of the function g as a function of x in terms of t. So, you have x to the I t over 1 plus I t times the product, which is exactly the product that came up in Delaunay's theorem. Times summation k going from 0 to infinity g of p raised to the k over p raised to the k. Okay, this is your, okay, this is the main term plus an error term which goes to 0. It is little o of x as x goes to infinity. Oh, 1 by x is here, so I just want this to be little o of 1 as x goes to infinity. Okay. In other words, as x goes to infinity, this function is asymptotic to this complex looking function. This error term just goes away asymptotically. The theorem that we had proved in the last couple of lectures can be interpreted as a special case of this theorem for t equal to 0. Okay. Now, if no such t exists, then what happens? This theorem answers that question as well. If no such t exists for which this series converges, then it turns out that 1 over x summation n less than or equal to x g of n tends to 0 as x goes to infinity. So, the mean value just turns out to be 0. Okay? Fine. So, this is, I'm not going to discuss the proof, but let's discuss an application of this, one potential application. Let us take the following function. G of n is the Mobius function. Now, what do you know about the Mobius function? At primes, this Mobius function just takes the value -1 at every prime p, right? So, can you show that this sum 1 minus real part of g of p, which is just g of p itself. So, that is 1 minus 1 times p raised to the minus it. Okay. So, you have 1 minus, so this becomes 1 plus p raised to the minus it over p diverges for any t in R. This is something I would like you to think about. For t equal to 0, it is very easy to see that this sum does diverge. For a non-zero, maybe I'll let you people think about this. What happens if you can show this? If you can show this, then by the theorem that we just stated, what we get is that if yes, then the partial sums of the Mobius function is little o of x as x goes to infinity. And this theorem about the partial sums of the Mobius function is in fact equivalent to the prime number theorem. Okay, this will follow. You can compare this to the other partial sums that you study, the smooth partial sums for prime number theorem. Use standard techniques like the partial summation. So, going back to the theorem of Wersing and Halash, I made a small typo. So, what I want is p to the minus it times real part of g of p. So, it is not real part of the product of g of p times p to the minus it. You are only considering the real part of g of p times p to the minus it, right. And so, this leads you to the question about whether you can find some t for which this series converges, or whether this series diverges for every t in R. Okay. Now, there is another nice theorem. These questions were studied in great detail, and you know, it almost feels like an overkill to use this theorem for a real valued function, because we are taking all possible complex valued functions, taking values in the unit disk and multiplicative, of course. So, here is another nice theorem by Wersing, which addresses those multiplicative functions which take real values and whose values are the values lie between in the interval minus 1 to 1. So, this is another theorem of Wersing. From around the same time, which states the following. So, what this says is that if you have a multiplicative real valued function taking values in the interval minus 1 to 1, then the mean value of g defined as limit, which we just defined as the limit of 1 over x summation g of n up to x, will always exist. Okay. And depending on certain conditions, we will be able to determine whether m of g is 0 or non-zero, but it will always exist. Moreover, this m of g is exactly equal to the following product 1 minus 1 over p times summation k going from 0 to infinity g of p raised to the k over p raised to the k. This whole thing is the Euler factor. Okay. If the following series 1 minus g of p over p converges, where p is running over all the primes, and in case this series does not converge, then the mean value is just 0. Okay. So, we can apply this theorem also to partial sums of the Mobius functions because they are real valued. Now, we do not have to worry about this p to the it and so on. So, for again in particular for g of n equal to mu of n, what do you know about this series? Summation 1 minus g of p over p. What is this equal to? It is 1 minus minus 1, so this is just summation 2 over p, which we know to diverge. And so, the mean value of the Mobius function is 0. In other words, summation mu of n up to x is little o of x. And an exercise for you. This is actually equivalent to the prime number theorem. So, you see your prime number theorem pops out as an example of this deep theorem of Versing. So, these theorems have many useful applications. Now, I would also like to indicate one more theorem in the same line of thinking, which takes us back to the detailed study of average orders of arithmetic function by using analytic properties of their corresponding Dirichlet series. So, in this direction, here is one more theorem that I would like to mention. Also due to Alash, it says the following. You see, the thing is, when you have a product of this form which is giving you the mean value of a function, the question is, what does it actually mean? What is it really giving you, right? This is just some product you see. So, how do you simplify this? So, this theorem says, so again let G be as before, G multiplicative, G of n, but it is a complex valued function. Okay. Then we are going to relate. So, given such a function, let us define capital G of s to be equal to the Dirichlet series coming from this function G of n over n to the s. Notice that since absolute G of n is less than or equal to 1, you can show that this series converges absolutely when real part of s is greater than 1, and in fact, by slightly more careful analysis, you can show that G of s defines an analytic function in the region when real part of s is greater than 1. So, let capital G denote the series, and what we know is that there exist, this is the statement of the theorem. So, there exist constants let's call them A and alpha, and a function which is what is called a slowly oscillating function. Okay, so it does not fluctuate very frequently. The oscillations are very, very few, and they take their own time. So, there exists a slowly oscillating function L of x such that, and these constants, such that the mean value of your little g can be written in terms of these quantities. This turns out to be, so the sum, I am just going to take x to the right hand side. So, the sum of g of n, the partial sums, is equal to x raised to the 1 plus I alpha over 1 plus I alpha times capital A times the function L applied to log x, okay, plus little o of x as x goes to infinity. So, your mean value can be written in this form provided something happens. So, the statement is not finished yet. So, mean value can be written in this form if and only if the Dirichlet series g of s turns out to be equal to a over s minus 1 plus I alpha times capital L of 1 over sigma minus 1 plus little o of 1 over sigma minus 1 as sigma goes to 1 from the right. Okay, if this happens uniformly for those complex numbers s, which are of course coming closer, and the real parts of which are coming closer and closer to 1, and what happens to the imaginary part? We want the imaginary parts to lie in bounded sets. So, if and only if this asymptotic holds as sigma goes to 1 from the right uniformly for t lying in minus m to m for any m. So, basically for any t lying in any bounded set of the form minus m to m, this asymptotic holds uniformly. If you can show this, this is equivalent. So, this is equivalent to deriving the mean value or the partial sums of g of n. So, this extends, this extends our previous study of understanding partial sums of arithmetic functions with the help of the analytic properties of their corresponding Dirichlet series. This is another theorem in that direction. Okay, it is a deep theorem, it is not an easy proof. So, I will not go into it in the class, but I wanted to show you one other connection between these sums and the Dirichlet series. Okay. So, this was a nice variety of what are called mean value theorems in probabilistic number theory. Now, let me give you some very nice and explicit examples of certain arithmetic functions, not necessarily additive, but here is something that some of you would have seen in a different context. So, let me recall some basic facts from the theory of uniform distribution. Now, a random variable. Recall quickly that a random variable real valued is said to have uniform distribution in the interval let us say 0 to 1 if the probability for any real number little x, the probability that capital X is less than or equal to x is the following, is given by the following density function, where f of t is just, it is 0 if your, so it is 1 if x lies between 0 and 1, and it is 0 otherwise. That is, the probability that capital X is less than or equal to x is equal to 0 to x dt, or that is, in other words, it is just equal, exactly equal to x for any x. This is just your uniform distribution. Now, uniform distribution, this term is also used in a different context of certain sequences whose limiting distribution function turns out to be the uniform distribution. Okay. So, a sequence, we consider a following type of sequence. By the way, before I talk about sequences and limiting distribution functions, some fundamental facts about this. Given your random variable which has a uniform distribution on the interval 0 to 1, what is the expected value of this random variable? What should it be? It is just the integral from 0 to 1 of t times dt, right? And so, this is just half. What about expected value of x to the k? So, these are the higher moments. What should you have here? By definition, this is just 0 to 1 of t raised to the k dt. This is just 1 over k plus 1. What about expected value of e raised to the it x, where for any real number t, what should this be? This is your characteristic function, right? So, this turns out to be e raised to the it minus 1 over t. Okay. This is something we record because now we are going to talk about limiting distribution functions of certain functions or of some particular functions, and the question is, what is the limiting distribution function of those in that scenario? And as we have learned from Levy's continuity theorem, that is equivalent to addressing what is the limit of the characteristic functions for those sequences, right? Do they converge to the characteristic function of the uniform distribution or not? That is why we have made a note of this, the expected value of e to the itx. So, now let us define the notion of uniform distribution modulo 1. Not to be confused with uniform distribution as we understand for random variables. So, what does this mean? So, we say that a sequence is uniformly distributed modulo 1. So, a sequence of real numbers, okay, and let us take positive real numbers or non-negative. Let us call it alpha sub n, is said to be uniformly distributed modulo 1, or another way to say this is said to have uniform distribution mod 1 if the following happens. The limit as n goes to infinity of 1 by n times the number of n up to n for which the fractional part of alpha of n, okay, so to avoid confusion between different symbols, so let me take this to be a sequence, any sequence of non-negative real numbers. So, if this limit of the fractional parts okay, turns out to be z for any right. What is the fractional part? By definition, it is alpha n minus its greatest integer. Okay, that is why we talk about distribution modulo 1, right. So, what is happening here? What you have is a situation where you are taking, so you have some sequence alpha sub n and your function, arithmetic function, is just the fractional part of alpha sub n. And we are asking, we are saying that, so we say that, so this has uniform distribution mod 1 if the limit law or the limiting distribution function is the uniform distribution. Okay. Now, what kind of sequences satisfy? So, this is another very important topic in number theory, and a very classical theorem of Hermann-Weyl states the following. which is basically, it looks very much like your Levy's continuity theorem applied in the context of this limiting distribution. It says he says the following, that a sequence alpha sub n is uniformly distributed mod 1 if and only if the following happens: for each integer m which is non-zero, the limit of the exponential sums alpha sub n turns out to be exactly equal to 0 whenever m is a non-zero integer. This is again a very important theorem. Before I give you some examples of uniformly distributed sequences mod 1, let me briefly indicate a proof of this theorem. So, this is an if and only if condition. So, to prove this, what do you have to do? Let us start with, let us prove the only if part. So, let us start with something that is uniformly distributed modulo 1. Okay, then what happens? So, in other words, your distribution function for the induced probability measures on the natural numbers up to capital N, what is that? So, 1 over n, basically the number of n up to n for which your alpha sub n lies in the interval 0 to z, which is the same as taking the sum over all those n's for which the fractional part is less than or equal to z, and for every such n for which this happens, add a 1. This is just another way of writing the counting function. So, because this is uniformly distributed, this limiting distribution function as n goes to infinity is equal to just z, which is the integral. So, it is going to the distribution function for the uniform distribution. So, what does that mean? By Levy's continuity theorem, the characteristic, an equivalent statement will hold for the characteristic functions, right. So, your phi sub f sub n of t, the characteristic function corresponding to your capital F sub n, it must converge to the characteristic function corresponding to the uniform distribution, right. But what is this actually? What is the characteristic function corresponding to f sub n? It is the expected value of e to the I t times your x n, where x n is your random variable given by alpha n for all the little n's up to capital N, right. So, this characteristic function is just equal to summation. So, what you have is one by n summation E of I t times alpha n, okay, for n. Actually, you should have fractional part of alpha sub n, but exponential is a periodic function. So, whether you take the fractional part or the real number itself, this gives you the same value. This converges to the characteristic function of the uniform distribution, right, which is, what is that? What you have is, so integral of e to the I t z, okay, times your just your dz, z going from 0 to 1. This holds for every t. In particular, you can take t to be equal to 2 pi m for non-zero integers. Take t to be equal to 2 pi m. M is a non-zero integer. Then what do you have on the left hand side? You will just replace t by 2 pi m. But on the right hand side, what happens? You have integral of e to the I 2 pi mz dz. What is that integral actually, if m is a non-zero integer? By taking t to be equal to 2 pi m, what you have is that 1 by n summation e raised to the 2 pi I m alpha sub n this by Levy's continuity theorem. If the sequence is uniformly distributed mod 1, then this is equal to the integral from 0 to 1 e raised to the 2 pi I mt dt. But if m is not 0, I leave it as an elementary exercise for you to verify that this is just 0 for any non-zero integer m. Okay. So, this is, I know some of you have studied uniform distribution in different contexts. So, this is to indicate to you how it follows, Weil's theorem follows as a consequence of Levy's continuity theorem. Now, what about the converse? Converse is harder. Okay. So, converse meaning you have been given this condition and you have to show something. So, what are you given? So, this part I am going to leave as an exercise, but let us at least discuss what we know and what we have to show. Conversely, we are given that the sum e raised to the 2 pi I m alpha sub n, this limit, this converges to 0 if m is a non-zero integer. Okay. And what do we have to show from this? We have to show, it will be sufficient for us to show that 1 over n summation n up to n of e raised to the I t alpha sub n will converge to e raised to the I t minus 1 over t for every t in R. You know this theorem to be true if t is of the form 2 pi times m for any non-zero integer. Okay. For m equal to 0, what do you have? This is tending to 1, right. From that you have to deduce that the characteristic function of these random variables converges to the characteristic function of the uniform distribution function. Okay. So, this is something I will let you think about. We can revisit it in our next class, but before we finish, let me show you a nice application of Weil's theorem. This requires, by the way, going from here to here requires some amount of Fourier analysis. So, in particular, let us take alpha sub n to be equal to n times theta, where theta is some fixed real number. Okay. Now, if theta were a rational number, right. So, what I am going to do is, so if theta, let us say it is of the form 1/3. Okay. So, what we are interested in the fractional parts, what will our sequence be? So, for n equal to 1, you just have 1/3. For n equal to 2, you have 2/3, since these are less than 1. So, the fractional parts are what they are. For n equal to 3, what do you have? 3 times 1/3, 1. What is the fractional part of 1? It is just 0. So, you go back to 0. Then you have 4 times 1/3. Okay, the fractional part is again 1/3, 2/3. You just continue in this direction, in this way. So, the sequence of the fractional parts of 1/3 take 3 distinct values. They do not seem to have a uniform type of a distribution. Okay. This you can immediately observe that this idea will generalize to any p by q. Any rational number of the form theta which is equal to p by q, the sequence of n theta will not be uniformly distributed mod 1, right. What happens, however, if theta is not a rational number? Let us say theta is of the form square root of 2. Then it is not so easy to figure out what is n times square root 2, what is the fractional part for every n. Okay, but the amazing theorem of Weil actually tells us that in this case, your sequence n times theta mod 1, or the fractional part, is in fact uniformly distributed mod 1. Okay, why is that so? If you want to apply Weil's theorem to study this, you have to study the sum 1 over capital N times summation n up to capital N, and then what do you have? E raised to the 2 pi I n theta. It is this exponential sum that we have to study, and in fact e raised to the 2 pi I m times n theta, okay, for where m is some non-zero integer, and we want to figure out what this converges to as capital N goes to infinity. So, this is a geometric sum, right, and when you sum up, so you have a finite geometric sum, what you end up getting is, so this is equal to 1 by n times, if you sum this up, you will have e raised to the 2 pi I, I will let you verify this, e raised to the 2 pi I m theta minus e raised to the 2 pi I times m times capital N plus 1 theta, okay, over, what do you have? 1 minus e raised to the 2 pi I m theta, okay. What happens to this sequence as capital N goes to infinity? Notice since theta is not a rational number, you know m is some fixed non-zero integer and theta is an irrational number, then e to the 2 pi I m theta cannot be equal to 1. So, the denominator is non-zero, right. So, let us take the absolute values of these terms. The absolute value, so you have absolute value of a non-zero complex number which is fixed, you do not worry about that. What about the numerator? Absolute of e to the 2 pi I m theta is at most 1, absolute of e to the 2 pi I m n plus 1 theta is also at most 1. Okay. So, the absolute value of this number here is less than or equal to 2 over absolute value of a fixed non-zero complex number. But then you also have 1 over capital N multiplied with it. So, as capital N goes to infinity, the absolute value of this term goes to 0, which means this sequence of complex numbers itself must go to 0 as capital N goes to infinity, and therefore, by Weyl's theorem, your sequence n theta is uniformly distributed mod 1 if theta is an irrational number. Okay. So, this is a nice application. We'll do some more examples of uniform distribution later on. So, the homework I give you for today is to figure out the other part of Weyl's theorem. Okay. Stop for today.